What's going on, guys? It's the Unhinged Engineer here, and today I have a bit more of a niche video than usual. However, I've gotten so much demand from my subscribers to make a video specifically about guidance, navigation, and control engineers within the context of aerospace that I thought I'd be remiss if I didn't dive into the deep end of the technical pool. So today I'm going to be talking about just a general intro to GNC engineering, like what it is, primarily focusing on the content, and then towards the end, kind of getting a little bit more into the career stuff that you're likely used to on this channel, where we talk about who should get a job in GNC engineering and why, and then if that's something you decide you want, how to get that job. So yeah, if you're interested in videos like this, or just more broadly, engineering career advice for other young professionals like myself, then you've come to the right channel. I'm the Unhinged Engineer, and without further ado, let's get into an Aerospace GNC intro for dummies. Okay, so first I'm just going to talk about, in the broad strokes, what is guidance, navigation, and control as a field. Once we've laid out academic themes of GNC, I'll then get into its constituent pieces, which unsurprisingly are guidance, navigation, and controls. Once we've gotten that out of the way, now we're going to start talking about whether you should actually get a job in GNC, and if so, how. Starting off, what is guidance, navigation, and control? GNC is a branch of engineering that deals with the design of systems to control the movement of vehicles. So if you think about all the software that's running on an aerospace vehicle, it's not just about controlling that vehicle. There's also stuff to do with communications and actually running the operating system of the flight computer, interfacing all the different components, reading electrical signals off of sensors. There's tons and tons of software on any given part of a flight computer these days. But the software that is specifically geared toward running and moving these vehicles or helping them complete the tasks that they were deployed for, that's what guidance, navigation, and control systems is really about. And if you take a class in this area and your professor's half decent, the first thing they'll show you is likely a chart like this. So this is a system block diagram, but it's more really just a flow diagram that kind of demonstrates how G, N, and C actually interface with one another. I'm going to go through this step by step, but all the way on the left here, we have guidance. So guidance is all about deciding where we want to go. So it's really about intent. Where do I want to go? That could be a specific position. That could be a specific trajectory that results in me getting to a position. It could be getting to an area and covering it in some way, if it's a kind of loitering aircraft or whatnot. Guidance is all about deciding where I want to be, and sometimes why as well, if you're getting a little bit more into autonomy and AIML, but that's the subject of a separate video. For right now, we're just going to say guidance is what tells you where you want to be. So if you look at this next kind of circle with an X through it, that's actually an addition operator, if you think about it, for these kinds of flow diagrams. And so we're subtracting something from that set point. Now, I'll get into what that means later, but for right now, you can just think about this system as saying there is a difference between where I am and where I want to be. And once you take that difference, you get your error, and you feed that error into your control system. So this gets to the second part here, which I'm going a bit out of order because I think in the context of how this actually works in the real world, it makes more sense to go GCN instead of GNC, but GNC sounds better, so I'm glad that's the acronym. Controls is all about taking that error that you're provided and imparting some force, whether it's a thruster, whether it's a control surface like flaps on an aircraft or other things. A controller is about imparting the physical force by whatever means the vehicle has available to it to drive that error I just described, the difference between where we are and where we want to be, down to zero. So a controller is coming up with the commands to do this, and those commands kind of manifest themselves within the physics of whatever process or medium in which you're moving. So plant is a bit of a weird term, but the reason it's commonly used is because in a simulation, your physics plant is really the model of the physics you have. So whether that's a model of aerodynamics, orbital mechanics, something else, your plant in a simulation is actually the dynamics model you've created to capture the physics of whatever process you're trying to control. In the real world, it's the actual physics. If you turn your flaps on an aircraft, air is going to start going over those parts of the wings at different rates, and then your aircraft's orientation is going to change in some way. So there's real physics going on as a result of whatever the controller decided was the correct command at a given moment. So your physics plant is really just stuff happening. If it's a simulation, it's stuff happening in sim. If it's real world, it's stuff happening in reality. Your controller sends a command. Depending on that command and the physics of the situation, something is going to happen. That something is then read by a sensor. So getting back to the plain example with the flaps, let's say you have an IMU on board. You turn your flaps, or I don't know if flaps is the right word, but you turn your flaps, the orientation or the altitude of that aircraft changes, and then that is picked up either by an IMU or an altimeter or other sensors on board. So the sensors are reading the situation, the physical situation, with some error of their own, by the way, plenty of error of their own. The sensors are reading that out, and this is why we refer to them also as a model, right? Because if you think about what an altimeter does, they don't just automatically give you an altitude. There's some post-processing that has to go into actually understanding the signal coming off the sensor and getting a good read of what your altitude is based on it. So you have some model of how your sensor behaves, and that may actually have some errors associated with it as well, like I said. So your sensor then reads out your measurement, and that measurement is fed to your navigation system. So what the navigation system is really about is figuring out where I actually am. So going all the way through this loop just one time very quickly, guidance decides where you want to be. Based on the error between that and where you actually are, controllers come up with a command to close it, and then navigation determines where you are at a current step in time. And so that navigation, this is why it feeds back into that kind of error operation that I have here. Navigation is what's telling you your current state. But hopefully your current state and your guided state, your desired state, your set point, the difference between those is small enough that we're comfortable with it. But if it's not, then that error is fed into the controller, and this process happens over and over and over again. So this is why more commonly than not, you'll hear the general kind of GNC loop be referred to as such. It's referred to as a loop because at any given point, it's saying, hey, where am I? How close am I to my set point? Let me impart some commands. So I drive that down. How am I doing? Okay, I'm doing better. Now I'm doing worse. Let me change my controller, right? So there's this loop. And then by the way, I forgot to mention, at any given point, your guidance could also change. Like maybe everything's working as intended. It's just where you want to be changes. So now your error is going to go really large because it's the difference between your old set point and your new set point. Okay, this loop is going to start over and over again. So this is why I very commonly refer to GNC as the GNC loop. It really does run like a loop on most real systems. So this is the broadest strokes of GNC. It's kind of the first concept I learned of this loop, and so really got me interested in it over the course of my undergrad education. So now that we talked about GNC as a whole, let's dive into some of the specific subcomponents. Starting off with guidance. So guidance refers to the determination of the desired path of travel or a trajectory. By the way, I should have said earlier, all these definitions are from Wikipedia. I just like using Wikipedia because they didn't let me in middle school. But using the Wikipedia definition of guidance, this is how it's described. So it kind of talks about a set point as well as desired changes, which kind of starts to sound like the controller piece. This is kind of something that lives at the border. How that error is calculated and actually fed to controllers, you could dictate as either being part of the guidance system or part of the control system. In any case, guidance is really all about setting this desired path or this desired state. A path is really just a set of states, so they're kind of the same thing. What are some relevant areas of guidance here? Well, a big one is optimization, mainly because a lot of these different path planning operations have some form of optimization associated with them. So a classic example is Dijkstra's algorithm, where you're using this kind of dynamic programming approach to calculate a bunch of costs on some grid. And then once you actually find the destination you were looking for, it then traces a path that's the minimum cost, so the minimum distance, back to where the search space originally started. So that's like a very classical example. I've done that in school. I'm sure many of you have as well. But there are other ones like, if you see at the bottom there, maybe we know where the destination is, and we kind of can draw a straight line in 2D, but when we take into account the terrain, there's actually other paths that may look longer in 2D, but are actually less cost based on vertical displacement. So optimization's kind of like the cornerstone of guidance in a lot of ways, not all the time. The next one is modeling and simulation. Honestly, mod and sim really falls into all of these, but it's just worth mentioning that guidance typically has one of the heaviest algorithmic loads here because things get really complicated. It's also interfacing with autonomy a lot of the time, which has very complex algorithms and processing associated with it. So mod and sim is just really important here because we have to validate that these algorithms are actually going to work when we fly it and stuff doesn't start cratering out of the sky or the atmosphere or whatever. The next one is game theory. So this is a specifically defense application, but oftentimes when we are trying to get to something and that something does not want to be gotten to, when there's this kind of pursuit evasion game going on, there's different kinds of algorithms and different kinds of trades you have to account for. Whether it's about minimum cost in terms of repellent, whether it's about observability between one party versus the other. There's lots of stuff that goes into these kinds of pursuit evasion games, as they're nominally referred to. So game theory is actually really, really interesting stuff that I've enjoyed over the course of my career. And then the last one is human factors and autonomy. And what I'm really just saying is that if you look at that chart I showed you guys earlier, the truth is there's one more box to the left of guidance, which I didn't put there because it's not traditionally a part of GNC. And that's who or what actually made the decision. And so for human-in-the-loop type stuff, that's obviously a human operator. But sometimes with autonomy, we have these decision-making models like state machines or behavior trees or stuff like that, that are then deciding on those different paths, and then the guidance system kicks in. So whatever comes upstream of the guidance system is obviously going to be relevant to it in some way, because that determines how it's going to operate. Next one, navigation. So navigation refers to the determination at a given time of a vehicle's state, which is classified here on Wikipedia as location and velocity plus attitude, which attitude is really orientation. So what angle and which are you pointing? Based, if you have a camera or something else, how are you oriented in space? So location, velocity, and attitude. So some relevant areas of navigation include probability and statistics is a huge one because sensors are incredibly noisy. Also, physics models like the plant I described earlier themselves can be noisy because if the state of your physical system changes enough, your model could stop working. So like a great example is if you're flying at sea level versus flying at 50,000 feet versus 100,000 feet, the aerodynamics of how your different control systems are going to behave and how your aircraft is going to move as a whole is pretty different. So a physics model might not be applicable in all of those equally. And so navigation is about understanding at the bounds of where our models aren't working as expected, where our sensors are not working as expected, they have errors associated with them. How do we actually make sense of all these uncertain signals we're getting? The next one is state estimation, which kind of gets at that making sense of things piece. State estimation is really about fusing kind of human subject matter expert understanding and intuition about a situation with real-time measurements of a situation. The idea here is really, we understand as engineers how a physical system should behave within some error bounds. And then in real time, as they're actually out in the real world, there are going to be measurements that may or may not align with how we expect it to behave. And so fusing these measurements over time, so we actually have a strong operating picture of how things are behaving and why, that's what state estimation is all about. Now, it may seem a little random to separate it from probability and statistics. And the truth is, you're kind of right. Like, state estimation is really 80% statistics. It just uses some other aspects of engineering, like actually optimization in a lot of cases, such as the Kalman filter, to ensure that our results are going to converge. So ensure that things are going to behave in the long run as we intend them to. Next one's target tracking. Again, kind of sticking with this defense piece here. So searching for, classifying, detecting, tracking target, anything where you're not just interested in your own state, you're also interested in the state of something else, that a lot of times can be referred to as navigate, especially if that's kind of the desired set point that you're trying to get to. Suddenly guidance and navigation take on this new meaning. And so the navigation piece is really about using our sensors to maintain custody of that target and drive the situation as a whole to the state that we want, which is probably an advantageous one unless we're throwing the match, for lack of a better word. And then the last piece here is computer vision and AI/ML. Again, kind of similar to the whole autonomy, like these new methods are making their way into guidance. Computer vision is a huge part of it because now we can infer more information from images or really any sensors, right? Like a lot of computer vision techniques apply to sensors in other domains, whether electromagnetic, RF, otherwise. Understanding how to actually use these novel techniques to get a better picture of what our current state is, or in the target tracking example, what the state of whatever we're interested in is really going to help us a lot in terms of better, smarter navigation. Next is controls, which is deceptively simple as compared to the other two, but gets pretty complicated. This is actually where I got my start in the whole GNC area. Controls refers to the manipulation of forces by way of steering controls, thrusters, etc., needed to execute guidance commands while maintaining vehicle stability. So I like this definition because it kind of wraps the other two up in controls. When we have a desired state and current state that are not equal to each other within some bounds we want to do something, so we have active control going on, we want to do something that's going to drive this system to the state we want. And coming up with and actually executing those commands is what controls is all about. So what are some relevant areas of controls? The truth is, control theory in and of itself is a large academic field, but it has a couple different bits and pieces to it that I want to break out here. So one I like to talk about a lot is signal processing. And the reason I say this is that a lot of similar methods, like the best one being frequency domain analysis, there's a lot of crossover in the methods between analyzing a signal, like an RF or electrical signal or something like that, and analyzing an actual physics plant that we're trying to manipulate in some way with a control system. So there's just a ton of crossover. As I've alluded to on this channel, my first job was, I don't know why I used air quotes, my first job was actually more so about signals processing than control systems, and I just used my controls knowledge for it. So definitely a ton of crossover there that helped me pick it up really quickly. Next one is optimization. Again, like in a slightly different way from guidance. So guidance is about setting a desired trajectory in an optimal way. Controls is about imparting a command in an optimal way. If there's multiple ways to get the physics to a state we want, we should probably pick the one that minimizes resource consumption, whether that's thrust or whether that's electrical power, whether that's strain on an airframe or other structures. We're trying to optimize in some way so that we can get the most bang for a buck in terms of control commands. That's what optimization really means here. Next is kind of kinematics and dynamics. And the reason for this is that we want to understand really strongly how the different control surfaces we can manipulate are actually going to change this physics system. Because without a really strong physics plant that I referred to earlier, we're not going to be able to control it accurately. And so kinematics and dynamics is really just a big part kind of that tip of the spear. Like it's the last piece. We really want to have a strong understanding of how what we do is going to manifest itself in the real world. And the last piece here is hardware in the loop. So a lot of times controls engineering will also involve actually testing it on real hardware. So real hardware has strange stuff like latency and hysteresis and resonance effects. Like there's lots of things that happen in the real world that are difficult to capture in simulation without going down the fidelity rabbit hole and never coming out. And so ultimately, the highest form of validation that we can do, sans an actual field test, is actual hardware in the loop testing. So you're not just running stuff in sim, you're running real flight software on real flight hardware to make sure things are actually going to behave the way you really want. So HITL testing is a huge piece of controls engineering. So we've laid out kind of the foundations of GNC. The next question is, who should get a job in it? I'm going to break this out pretty simply here. I think whether or not you'd be interested in GNC is a very simple question. First of all, do you like math? And I know if you're studying engineering, you probably like math to some degree. But what I'm trying to get at here is, if you're the kind of person sitting in your advanced math class saying, man, oh man, I can't wait to graduate college so that I never have to do chalkboard math again, GNC is not the field for you. There are lots of other fields of aerospace engineering that once you get out of school, it's more about the tools and it's more about the applications than the actual academic knowledge. And GNC does go that way too. But when I think in my head about which fields of aerospace really stress that kind of academic knowledge that you got in the very beginning the most, few rival GNC here. GNC is really math heavy. You will be using what you learned in school a lot every day. And so if that's something you want, then this is definitely a great field for you. Aside from the math piece and the physics piece, there's then the computer piece. So if you're not a programmer, I don't think that GNC is really going to be a good fit. And the reason I say that is because, as much as like I mentioned at the end, controls engineers do hardware in the loop testing, when I refer to the field of GNC, we're really talking about software. We're talking about the software running on these vehicles that actually controls the vehicle in such a way that we want for whatever mission that it's being geared towards. So to do that, you have to know how to write this software. You have to know how to write algorithms. You have to know how to run simulations. You have to understand how they're actually going to run on the real vehicle. That's a whole dynamic to it that involves lower level programming than a lot of people think when they're getting into it. And you have to know about the actual electrical components themselves. So this is all to say, like, you really got to be a techie computer person if you're going to get yourself into GNC. So if you are this person, if you really love combining physics and software, I would argue that there are a few fields as good for you as GNC. I think it's really strenuous. It's really academically rigorous. It's hard. It's interesting. And some of the smartest engineers I've ever met are GNC engineers. I've worked as a GNC engineer. I've worked adjacent to GNC engineers in several ways throughout my careers. And man, oh man, are they seriously very smart. So if you're interested in combining physics and software, I think this is a great option. And then to wrap up this incredibly long video, how to get a job in GNC engineering. So I don't think GNC engineering is that different from any other field of aerospace. I'm not gonna spend too much time talking about this, but just to lay out the foundations here, right? The first one is obviously take the really advanced math classes that I refer to as being skills you're gonna need. So take calculus, take differential equations, take advanced linear algebra, take some of the fancier stuff beyond that, like electives. Really get into the difficult math classes, and where possible, because I know in school it's kind of hard to get good high-level coding education these days. Do the same thing for coding too when you can. Like stress the academic piece as much as possible. One thing I forgot to put in these slides that I'm going to highlight here. There's a big debate about whether or not you need a master's degree to do GNC engineering. Most of the time, people who get jobs in GNC do have masters. There's a reason for that though, which is most course, like kind of academic plans, don't actually stress GNC topics until the tail end of senior year. So there's a lot of people who don't actually figure out that they want to do GNC because they didn't get exposed to it early enough until the very end. And so they go into a master's degree, they get really deep subject matter expertise with those advanced classes, and then that's how they break into GNC as a role. I'm just gonna say, like, I have definitely seen master's degrees help significantly getting GNC roles, and most GNC engineers do have one, but that is definitely not a hard and fast rule. Like, there are lots of exceptions. There are lots of people who have worked in GNC or adjacent to GNC and don't have masters, myself being one of them. So it's definitely not a hard and fast rule, but it's just worth noting, like, master's degrees do definitely help you get a GNC job if that's something you're really serious about doing. The next one is just knowing the tools. One thing I'll say is, like, at the end of the day for GNC, you're gonna have to know how to write C++. It's just the reality of how flight software is written and how lots of 6th degree of freedom simulation frameworks are written, because, you know, those are very compute intensive, and so they got to be performant. Aside from that, MATLAB or Simulink is also good, and just programming as a whole is really important. But you got to learn C++. I danced around it for so long ultimately to realize, hey, this is what employers want. You just got to go out and bite the bullet. So definitely learn C++. Next piece here is get the experience. So obviously a GNC internship is the ideal case. So that's what I did. But there are other types of internships or even full-time roles like flight software, like modeling and simulation, which is something I've done before. There are lots of different roles in those two, as well as just software engineering at aerospace companies writ large, that will help you work your way towards getting a GNC role for sure. It's not like once a non-GNCer, you're doomed to never have a position in it. Like, I think people get a little elitist about it because GNC is a very prestigious role, but that doesn't mean that you can't do other things and then come back to it. There are definitely lots of ways to break in that is not so traditional. I went through undergrad and then straight to a master's and straight to a GNC job and never looked back. Like, don't underestimate the value of adjacent fields for sure, especially as somebody who spent the majority of the career in them. The next one is HITL testing. So this has actually been a weak point for me historically. Like, I am a purely software guy for the most part. I mean, I build stuff in my spare time, but in terms of work, the majority of my work has been focused purely on software. Knowledge of how to interface with and actually test real hardware and validate that your algorithms run on the real hardware the way you want is a very desirable skill that I think lots of employers love. And that kind of hands-on applicable knowledge is something that you can't get in a classroom. So again, if you're being lean and mean on the academic side and want real-world application, HITL testing is a great way to do that because it's more broadly part of this integration experience. Like, GNC has lots of really complex moving parts to it. And so demonstrated ability to interface and understand the relationships between all of them is hugely desirable. The last thing I'll say, not to end on an ominous note, but GNC interviews are some of the hardest interviews I've ever taken. And the reason is because they combine aerospace knowledge with programming ability. So if that sounds like a nightmare combination, that's because it is. So lots and lots of preparation goes into crushing GNC interviews. I can make a video about this at some point if we want to get even more niche than this video already has been. But I would just say study your stuff, study your courses, think about the different kinds of questions that you might be asked related to that coursework, and do a crap ton of coding practice and preparation. Maybe that's building stuff. Ideally, I've made videos about learning through projects. I think that's better than just leak code, but there's also a certain level of just having to be able to write algorithms on the spots that you may be asked to do. So yeah, definitely lots of prep to do there. But that's pretty much it. I just wanted to make this video about GNC. To be honest, I was kind of putting it off because making an entire dedicated video about one specific field of aerospace engineering, I don't know how well this is going to perform, but I've just gotten several questions from several different subscribers like, hey, I'm interested in the kinds of things that I've alluded to on this channel, being GNC or GNC related. You know, people seem interested in that, and it's a bit of a niche field that there's less information about than others. So I just wanted to make this video kind of breaking it down. Yeah, I hope you enjoyed. I'm the Unhinged Engineer. I make professional development content for other engineers like myself. I also talk a lot about aerospace because that's what I do primarily. If any of this stuff is of interest to you, then I would definitely recommend you like, comment, and subscribe. Thank you so much for watching, and I will see you next time.